All right, welcome everybody. We're going to be talking about Lincoln lists, like Lincoln logs, but they're Lincoln lists today. So, this is where we were when we left off last time. In the previous class, I did talk about this thing called a trigraph. Some people were excited about C++ 23 coming out. Compiler support is not quite there yet for a lot of the stuff. G++ supports some of it. The thing that excites me the most is the ability to just write like import like that and just bring all of the standard library in like that. Like would be fantastic. Only Visual Studio has that implemented currently. So students were asking like, do they ever take things out of the language? And so there's this thing called a trigraph. And so if you were to see out Nani, you dare approach me. What do you think this is going to print to the screen? What do you guys think? What is this going to see out? There's a warning on it. I think it's going to print. Honey? So Tothan says it's going to print out Nani with a vertical slash. However, it prints out just Nani, question mark, exclamation mark, which is what you get for attending the previous class. It works just fine. It's just question mark, exclamation mark. Like that's all it is. Except, if we compile this with an older version, std equals C++ 11 or whatever, then you get a vertical slash here. And so this is actually an example of something that was deleted from the standard. The whole trigraph thing is this weird artifact from the 1970s when like people didn't necessarily have every symbol on their keyboard. And it's like some people didn't have a vertical slash, and so you'd have to enter a vertical slash by doing question mark, exclamation mark. And if that sounds stupid to you, it probably made some sort of sense back then when you wouldn't be able to type that, right? You'd have to type like, like that, and it hasn't been an issue for like 40 years or something. But like IBM, from what I understand, fought tooth and nail to keep it in because they had it in their code. And I think they just didn't want to have to do the search and replace to replace every instance of Nani, with that. But like you could just type this accidentally, right? And so like all sorts of people would just type, and then like you'd get a vertical slash coming out, and there's lots of these things like I don't know, it's like parentheses or whatever. And so that's like closed bracket and things like that. So there's all these weird things. And so that's a little bit of C++ trivia right there. It's no longer in the language. They actually deleted them out of the language. I think in 17, C++ 17, I think finally eliminated trigraphs from what I recall. Like just IBM, do a search and replace. That's all you got to do. All right. So we're going to talk more about linked lists today. And the, last time we talked about how to like search through a linked list. This is our list traversal algorithm, starting at the head until it hits null. Go to the next one. If you match a value, return true, otherwise return false. This inserts at the beginning. So how do we delete something? Okay. So let's actually sketch it out. Let's whenever you work with linked lists, I think it's highly valuable to actually draw the linked list and kind of see what's going on here. So cool, look at that. There's our linked list. Okay, our head's pointing at 512. So if we're going to delete the head, what should happen? Like what exactly? We should have a delete command, right? Are we done? Is that all we have to do? What do you guys think? What's really interesting about drawing it out is that every time you have ink, every time you put ink on your figure, that usually translates into like a line of code. So this crossing off of 512 here is going to be like delete head, right, or something like that. So are we done? Is this a valid linked list now that we have unallocated 512? Is everything looking right? Do we have any dangling pointers anywhere? Does this look good to you guys? What's wrong with it? Yeah, we got to set head to the next, right? And if you delete head first, then you can't say head equals head points to next, because you've already deleted it. Never use code that you've deleted. Never use memory you've deallocated. That is a highly dangerous and suspect activity. But if we moved the head to point to here first, then how do we delete this guy? So what's our solution here? Like if we said head equals head points to next, we do that, then we have no way of deleting this. So how should we resolve this conundrum? We need to both delete the first element and make a copy of it somehow, so we can make either write down this one somewhere or write down this one somewhere and move head and then delete. Head would be pointing. Remember, a pointer is just an integer. It's just an integer. Imagine that this memory address here is 700 and this one's 600 and this one's 6 million and then this one's like 20. When you have a pointer to something, it's literally just like head is equal to 700. And so if you say delete head, it unallocates that RAM there, but head still holds the value of 700. It does not set the pointer to 0. It doesn't, like, some people try setting a pointer to 0 to delete it. That doesn't do anything. You actually have to call the delete command to delete something. And really, I think it's helpful to just think of an integer, like a pointer as an integer. Because that's all it is. Like, there's nothing special about a pointer. It's literally just a number. And it's just saying at that memory address over there, this node exists. And now that memory address at offset 0, so at memory address 700, it's going to hold the value of 512. And then at memory address probably 704, it's going to have a pointer to this guy here, because the integer is 4 bytes. So yeah, so how do we resolve this? How do we make a copy of head so that after we move head to here, we can delete the old head? Make how pointer visually are like address. Pointer technically holds a value, and the address is where the pointer is located. The address is where the pointer is located. The address is the value held in the pointer. So the pointer holds this memory address of 700. Just kind of like how x holds the value of 5. The pointer here holds 700 in it. Is it technically possible for two different nodes to point to the same node? Yeah, you could. You could have that guy pointing at that guy and that guy pointing at that guy. It's not a linked list anymore. So you've probably screwed up if your linked list looks like that. But yeah, in CSI 26, you'll learn about things called graphs. And everybody can point to everybody else and stuff like that. Yeah, this Spider-Man, pointing meme, right? So yeah, pointers are kind of important. All right, so what we're going to do if we're going to delete something is we can do something like this. We can say like node pointer temp equals head. Head equals head points to next. Delete temp. And there we go. So what this is going to do, the first line of code is going to say temp equals head. So if head holds the value of 700, what value does temp hold? Making a new variable called temp. It holds memory addresses. It's going to hold the value of 700 also. So we visually draw it as like pointing at this thing, but all it really holds, it's just an integer, really. If you like really look under the hood, it's just an integer, and it holds the value 700. So it just copies the value. Like head is just holding, we draw with all these arrows and stuff. It's just the number 700. That's literally all it is. So when you say temp equals head, it just copies the value of 700 into temp. And then when you say head equals head points to next, the point operator is going to grab that memory address there, which is 600. And so when you say head equals head points to next, that puts the value of 600 into head. It just copies the memory address is literally just an integer. That's all it is. And a 64-bit integer because we're on a 64-bit system, but it's just an integer. And so the way we draw this is we draw it as head is now pointing at this guy. Okay. So when we say head is equal to head points to next, then head was here. Then we copied the value of like this memory at this guy here, this pointer here is literally just the number 600. Like we draw it visually as an arrow because we actually don't know what the memory address is. I'm just making up memory addresses here. But like literally this pointer here is just holding the value of 6 million. And this pointer here holds the value of 20. That's all a pointer is. A pointer is just an integer. And so you just copy a pointer from, one to another. And so we said head equals head points to next. We went from pointing at this guy to pointing at this guy. Right? If you want to look at the quiz for today, you guys did pretty well on it, but we'll look at it real fast. 62 people did their competency exams yesterday. All right. So if you have A pointing at B, pointing at C, pointing at D, and head's pointing at A, then head points to next is B, that points to next is C, so it's going to print C. Yeah. Technically, it would be next points to data, but you know what I mean. And then for this one, if head is pointing at A, then head points to next is B, points to next is C, points to next is D, 3, points to next is a segfault. Okay, probably. It's not guaranteed you're going to segfault, but yeah, you're going to segfault. On our system. On our system, you will segfault. Okay, and then the main advantage of list have over vectors is that they are faster at inserting and deleting in the middle of a data structure. Well, you got a pointer there. If you insert into a vector, or if you insert at the beginning of a vector, then it's got to move all the elements out of the way. So, which is an order n operation to move everything out of the way, and you put a thing in the middle. A linked list you can add at the beginning, no problem. You can add at the end, no problem. You can add in the middle, no problem. If you have a pointer there already. Now, the downside to a linked list is that if you want to go to let's say you have a linked list of size like 1 billion. Like you've got 1 billion nodes. This guy points at this guy, 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 points at this guy. And you want to go to element 1,000. With an array, you could just be R square bracket 1,000. Boom. Order 1. Access. How many operations does it take? Answer now on chat. For you to get element 1,000 out of a linked list. You got a pointer to the head, you got a pointer to the tail. Maybe it's a doubly linked list, you can go both ways. Can you just jump to element 1,000? No. Not unless you have a skip list or something like that. There's some data structures that have pointers that jump 100 ahead and 1,000 ahead and things like that. But in just a normal linked list, no, you guys are all right. 1,000, you have to go to the next, Or technically 9999. Yeah, sure, whatever. Because you have a pointer ahead. Whenever we're talking big O, we don't care about minus ones and stuff like that. So yeah, technically you're right. Technically it's 999 guys to the right to find element 1,000. You cannot grab based on the index. Yeah, there is no random access in a linked list. That's the huge downside. And what's more important depends on your application. If your application is going to be inserting and deleting from the middle a lot, then probably a linked list is going to be better. If you're going to be inserting at the end a lot, probably a vector is better. It really depends on your application, and that's what this class is about. This class is about teaching you the basic data structures, so that when you're given a task and you're okay, for this task, we're going to be inserting at the front and inserting at the back a lot. You're okay, the right data structure to use is what do you guys think? If you want to, yeah, a queue, at the DMV, right? So you're inserting people at the back of the queue, right? So as people come in, they go to the back of the line, right? And then they come out the front of the line, right? So what data structure should you use? A vector, a linked list. Can you turn linked list data into an array? Yeah, you can just iterate over a linked list. In fact, that's probably how I would sort a linked list. Because sorting a linked list is annoying. It's actually really annoying to sort a linked list. I would actually probably just copy all the elements in a linked list into a vector, sort it, and then make a new linked list out of that vector. Just so that I wouldn't have to actually implement a sorted. There are sort algorithms that work on linked lists, but they're obnoxious to write. So I would just copy it into a vector, sort the vector, and then make it back into a linked list. a vector? No, vectors are bad because you would be deleting off the front every time. Every time you would delete from a vector off the front, you'd have to shift all of the elements forward by one. And so you'd be doing in order n operation. So if you had a billion people in line at the DMV, which is, your normal Wednesday, then you would have to do a billion squared operations, which is bad. Now, it's the DMV, so maybe slowness is a feature, right? So I don't know. You got your sloths running the DMV, so. I've lost my tablet. So maybe they do design it that way. I don't know, but yeah, a linked list would be better than a vector, because linked list, especially with a doubly linked list, you can insert at the back, pop off the front, order one for each operation. However, the vector linked list choice I would make in such a circumstance, singly linked lists are terrible, because if you have a tail pointer and you delete the last element, there's no way for the tail to move backwards by one. Do you guys understand? It's like singly linked lists are terrible. Like overall, they're just terrible. The only reason why I'm showing them to you here is because it's less drawing. There's just less ink on the screen. Like, think about this, right? You've got like a tail pointer here, and you delete this guy. How do you move the tail to here? You can't. That's why you have a doubly linked list. A doubly linked list has a previous pointer, and you just move the tail back. What you have to do when you delete this guy is you have to now iterate across the entire damn thing from start to finish, and then set the tail pointer to be there, which is absolute garbage. That's order n deletes, which you do not want. You do not want. If you're using a singly linked list, you are only pushing and popping off the head. You're not pushing and popping off the tail ever. Or you're doing it wrong. You're just doing it wrong. I mean, you could, but you're doing it wrong. So how do you sort a singly linked list? I don't think you can. I would convert a singly linked list. I would convert a singly linked list into a vector, sort the vector, and then convert it back into a linked list is what I would do. The standard linked list sorting algorithms, I think, work on doubly, but not on singly, from what I recall. So yeah, singly linked lists are just trash. They're just not good at almost anything. So okay. So the data structure I would use, though, if I was going to be doing a queue, is I'd use a deck. Okay, so a deck or a double-ended queue is my data structure of choice for such things, and it looks like this. Deck managers and and so a deck is just like a vector, except it's got push front and it's got pop front, and it's got push back like a vector, and it's got pop back like a vector. So vectors do not have these two things here, okay? Because they're terrible. They're order n for a vector to push and pop off the front, to insert and delete off the front of the vectors order n. With a deck, decks are order 1 for pushing and popping off the front. So if you're doing a queue, a double-ended queue is the data structure I'd use. There's also a queue class that's literally designed for queues, but the queue class sucks. I'd use a deck instead. So that's what I would do if I was implementing a line. Queue isn't good what it's designed for. No, queues are garbage. The queue class and the stack class are garbage. They're garbage classes. So yeah. Deck is the way to go. Deck is the way to go. All right. We'll talk about queues and stacks later. Would it only be good for the fundamentals? No, I would literally never use a stack or a queue in any of my professional code ever. They're terrible. They're maybe there for teaching or something like that, just so they can say they have a stack class and a queue class, but they're terrible. Okay, so let's come back up here. So what we're doing is we made temp equal to head. We said head equals head points to next, and then we are deleting temp. Bloop, bloop. Just like that. Temp equals head equals head points to next, delete temp. You guys see that? So head was originally pointed here. And like I said, every bit of ink you put on the paper translates into a line of code. So temp equals head equals head points to next, delete temp. And then we're done. When does temp vanish? Temp is just an integer, right? So when does temp go away? The actual pointer temp, not the thing that it's pointing at. When does the actual pointer go away? Do you guys remember when variables vanish? Ellen, what is the lifespan of a regular stack allocated variable, which is what temp is? When do variables die? What's the end of their lifespan? For a regular variable like a pointer or an int. At the end of the function. Yeah, technically at the end of the scope they're in, right, Ella? So you're right. Here it's the end of the function where it will go away. And so what happens is when we hit that closed curly brace there, then temp vanishes, and we're, oops, too much, delete. And we're looking good. So when you sketch everything out, head's pointing here, and all that's pointing here. Okay, looks good to me. Okay, so let's talk a little bit about doubly linked lists. Okay, so doubly linked list has a previous pointer, and the previous pointer on this guy. Wait, it's all backwards, isn't it? Here, let's just erase everything and start over. Okay, so a doubly linked list, which is what we usually use when we have a linked list. We're gonna have like some data. This might be strings, let's say. So we got boss here. We can have a previous pointer, which points at the person previous to us in the list, and we can have a next pointer, which points to the person after us in the list. Okay. And so if we have a single element in a doubly linked list, it's going to look like this. And we're going to have a head pointer, and we're going to have a tail pointer. And it's going to look like that. Now, what should head and tail point to if there's no elements in the list? Like, what would head and tail point to? And we're probably going to have a size also, right? Size is 1 right now. So what should head and tail point to if the list is empty? Null. Very good. Yeah, so if the list was empty, then it would be pointing over at null, right? 0. Okay. But with one element, it's going to look like this. Now, let's do this in code, because doubly linked lists are much more useful than singly linked lists are terrible. So CWay, I don't care about you anymore. Next, and previous. And next, okay. And node pointer new previous equals null putter x next and previous new previous. Okay. Now you can see the downside to null pointer being so darn big. If we used a 0 here, it'd all fit on one line. So. There we go. causing nerd rage in the C++ purists. Hey, it fits on a line now, right? Okay. This is the correct way of doing it, right? And probably we should initialize that to 0 also. Okay. Although it doesn't matter because our constructor's covering all those test cases anyway. Okay. So we need to have a head pointer that is the beginning of the list, and we need to have a tail pointer that holds the end of the list. If and only if, right? You guys understand? And then we probably should have like an integer for size or something like that. Holds how many elements are in the list. We technically don't need that. Every time we ask how big the list is, we can start at the beginning and iterate across all billion elements to get to the end to get the size. That seems like a bad idea to me. It's probably better to just write down how many elements you have. Okay, so what sort of class invariants do we have? What sorts of promises do we make with our private member variables here? Like, what sorts of things must always be true? Well, actually, I've already given it to you. Size must always hold how many elements there are. Head must always point at the first element. Tail must always point at the last element. So these are my invariants, actually. These are the 3 invariants for the class. Just right there in the comments. Those are things that must always be true about the class. Size must always hold how many nodes are in the class. In the entire list. So insert is good. Head is next. And then previous can be left as null. That's fine. We can call this, instead of insert, we can call this as like push front. And then we can also do a push back. Insert at the end of the list. So the previous of us. Okay, so the next is going to be null, right? If we're adding to the end of the list, right? The constructor says the next is the second parameter here. So we're inserting the value. The next is going to be null because there's nobody after us, and the previous is going to be the previous tail, right? And then the tail is going to move to the end. So if we do a pushback, let's run through this. 1 line of code. So let's say we do a pushback, right? And so we're going to insert, like Lewis or something like that. So the data is going to be Lewis. I always sketch things out when you're working with linked lists. So the next on this, who's after Lewis? What do you guys think? What should Lewis's next be? It should be null. Okay. Now, what should our previous be? We need a line of code for that. See, by sketching this out, we're like, oh yeah, we need to actually hold on to that. Because what's going to happen is tail is going to be pointing at the new guy here, right? But we need that set, and we also need this set. We're not currently setting those 2 things right now. Actually, I think we're setting the previous. Yeah, right here we're setting our previous to be tail. But this one's done. This one's correct. That one's being set properly. But we're missing this guy. So the artist formerly known as tail, his next should be set to be us. And so we could say tail points to previous points to next equals tail. How does that make you feel seeing that? Tail's previous, his next is equal to tail. And so that will do that right there. Just like that. Whatever you say. So tail's previous pointer, the artist formerly known as tail, his next is the new tail. Right? So the former tail. And if you wanted, we could have done this like this. We could have said like node pointer former tail equals tail. And then we could say former tails next equals tail. Something like that. Your brain hurts. And then we need to do the same thing for up front now, right? Because the previous head So head is equal to new head. Okay, so head points to next, points to previous equals head. And so the previous guy, when we push at the front, this thing's doing this thing again. It's doing this thing again. Okay. So if we're pushing at the front, then we need to, let's say we push Garcia at the front. So this is the new guy. The new guy's next is the old head. And the previous guy, the old head's previous is us. And so that's the code. Our next is the old head, and the old head's previous is us. And the old tail is tail points previous. Their next is us, like that. It should hurt your brain. The only way of getting good at linked lists is to practice them. Okay. I need to close double quote here. That's almost a disaster. Okay, and then what else are we forgetting? What's the point of doing this? We're making a doubly linked list, Tofin. We're adding the ability to insert at the beginning of the list, and we're adding the ability to insert at the back of the list. And so we can grow the array, the list one way, we can grow it the other way. So we can add to the front, add to the back. And then the head, of course, is going to be pointing here. Okay. What invariant did I forget? What invariant did I forget to update with this code? We have 3 invariants. Well, we have 1 for head. There's actually 2 invariants that I forgot in both of these. Okay, we've got head, we got tail, we got size. Here I am changing the list, and does the word tail appear anywhere here? Does the word head appear anywhere here? I've got 3 invariants. Every time you change your class, you must look to see, am I handling invariant number 1 correctly? Am I handling invariant number 2 correctly? Am I handling invariant number 3 correctly? I'm actually violating 2 out of my 3 invariants with this code in both of these. Am I updating the size? I'm adding to the list. Am I updating the size every time I add something? Do you see the word size ++ anywhere within this code? No, but I should be. You're absolutely right. And so I should do something like this, size ++ on both of them. Now that invariant is being kept up to date. My remove, just come in here. My remove will need some sort of like size minus in there as well, right? But let's do, instead of remove, we'll do like pop back or something like that in a second. Why size on both head and tail? What do you mean size on? Because size is the number of people in my list, right? I'm trying to keep track of how many people I have on my wedding list, right? And so right now, size should be 3, right? Because I got Garcia, Voss, and Lewis, right? And I was not updating it. Every time I add somebody to the list, I need to update my size. Size is how many people are in the list, and I was not doing it. I'm doing it now, but I wasn't doing it before. So then there's one other thing. Which invariant am I not updating here? And this is a skill that you can learn by TAing. Actually, you can look at a lot of bad student code and get good at doing this. One of the invariants, I can tell you right now, my code is wrong. Tail appears nowhere within push front, and so I guarantee you this code is wrong. I don't even have to like read it and understand it or any of that stuff. This code is wrong because tail starts off as null, and if I keep pushing and pushing and pushing and pushing into this list, tail will still be null, which is wrong. Tail must get updated to be head if the size was 0 before. So we need to do something like this. If size is 0, then tail equals head. There. Same thing for this guy over here. If size was 0, then head equals tail. Okay. So if we are adding to an empty list, that's when you're pushing at the front, right? Every time you push to the front, head moves with it. Tail stays the same. The only time tail will change is if you have like a completely empty list, right? And the very first time you add something, then tail will point to that. And so this code is now correct, I think. Okay. So let's do print. Oh, that's fine. Let's do delete. Delete from the beginning of the list. We should also have getters, right? Probably the getter. So int get, I would just call it front. Const method, return head points to x. If not head, throw runtime error. You dereferenced a null pointer. So front will give you the value at the beginning, returns value at the beginning of the list, back returns the value at the end of the list. Push front adds something to the beginning of the list, push back adds to the end of the list. So what I'd like for you guys to try and do now is code to delete from the front of the list. I'll give you guys 10 minutes to do this. So we're going to make a function called, it's not going to return anything, it's just called pop front. And we need pop front and pop back, and these are going to be pretty similar to each other. Delete first element in the list. Delete last element in the list. Okay, I'm going to pause the program for 10 minutes, and then we'll come back, and then I'm going to show you guys how to like look at code at kind of a high level, and see if I can get you guys some Jedi powers where you just like look at code and go, oh, it's wrong. Okay. So yeah, this deletes head and moves head to the right, basically. This deletes tail and moves tail to the left, or however you have it lined up in your brain. Okay. All right. You guys got 10 minutes. Begin. All right, let's take a look. So remember, there's 3 invariants: head, tail, and size. All 3 of those probably need to be in every non-const function. So I don't see size in either of these, so I can just immediately know that you're violating the invariant that size is always correct. Right? If you have 7 elements in your list, then size should be 7. If you delete off the front, the size is still 7. And so the size invariant's been violated here. I can say that without even like reading it closely. Okay. Head, old head equals head points to next, delete old head. Close. This is very close. So let's sketch it out. Let's see what this is actually gonna do. So snap this over here, snap that over there. Okay, so we got our minimize my face. And let's see if we can minimize this. There we go. Okay. So we're trying to delete the head right here, okay? So this code says old head equals head. So we're going to have old head, and it's going to be pointing at the current front of the list. And head equals head points to next. So this guy is now going to be pointed here. And then delete old head. Bloop, bloop. So that's pretty close. Do you guys see any problems with the list now? And in addition to the size not being updated, size should be decremented down to 2. Is there any problems you see on the screen here? You do have a new head. Head is actually correctly set to the front of the list. There's actually 2 problems. One, you're not handling if the list becomes empty. Right? If you have an empty list, then head and tail need to be set to null. The other problem is this. Head points to previous should be set to null. Very good, Ella. So that guy is currently a dangling pointer. The current head's previous is pointing at unallocated memory now. And that is a legitimate problem. Okay. So, good. Close though. If tail points to next equals null, which it always should be, tail's next should always be null. Delete tail. That will also segfault. If your list is empty, tail is null. So doing tail points to next is going to kill your program. So this is like a segfault waiting, and you're setting equal to null too, which is not probably what you expected. You probably meant to say double equals here. Yeah. All right. Let's see what else. Yeah, let's just do it. Okay, so what we need to do is we need to decrement size. So size is going to have to go down to 2. Head is going to have to move to here. Every one of these bits of ink I'm drawing turns into code, right? So size is going to be size minus minus. Head's going to be equal to head points to next. We're going to have to deallocate the old head. And this is going to have to be fixed as well. Okay. So let's do it. So if we're going to delete off the front, if size equals 1, so if we are deleting the last element, we are going to delete head, or we could say delete head, tail. Either way, it doesn't matter. Head equals tail equals null pointer, and size equals 0. And return. So handle the invariant, right? Like if you've deleted the last element. Also, if size is 0, just throw maybe. Yeah, throw. Runtime error. Can't pop from an empty list. Something like that, maybe. And then in the normal case where you've got stuff going on, then we need to do size minus minus. Node pointer temp equals head. So make a copy of the head pointer. Head equals head points to next. Delete temp. And then heads previous equals null pointer. And then that's a delete right there. Yeah. Right, so all those things that we did in ink. So heads previous equals null. Set that equal to 0. Okay. So let me fire up some code for you, and we can go through this, and maybe will help you thinking about it a little more. So whenever you have code, there is kind of like the core functionality, right? The core functionality of deleting that we just did is to delete, right? Like if any of you had not a delete in there, that'd be bad. It looks like everybody basically had a delete of the 3, 4, 5 people that actually posted things. Aaron didn't post anything. Caleb, like a lot of people just didn't submit any code at all. I see you all. I see you not submitting things. So, well, I'm sure the professor will show me. The whole point of lab time is for you to try and do it yourself. Like that's the best way of learning. It's to try and to fail. Like it's way better that they submit code that like Garcia did, that didn't work, so you can learn from it. If you just sit there and just like go eat a sandwich or something during lab time, you're cheating yourself. There's 17 people on stream right now, and 5 of them posted code. So Raphael was one of the 5 that submitted code. So good job. Seriously, I actually mean that. 12 out of the 17 didn't submit anything. Yep. So the class invariance. Okay, so there's the core functionality, and I'm going to code that in like gold, like the delete, right? And everybody had the delete, right? That submitted their code up here. So that was good. You're driving, that's fair enough. And I know that like the 2 Salas are sharing a screen or whatever. I'm not like mad. I'm just saying like if during lab time you need to be asking questions and like submitting code and writing code. You can't get good without writing code. So then what I've done is I've color coded the invariants, right? So we had one invariant that the list size always has to hold how many nodes are in the list. Head must always point at the first element in the list, or if the list is empty, it points at null. And then the tail pointer I'm color coding as blue. And so every member function needs to have some sort of core functionality in it, right? And then any non-const method, remember a const method is a method that doesn't change the class. If it doesn't change the object, I should say, if it doesn't change the object, then you don't need to worry about the invariants. It's fine. Like if you're not changing the class, then the invariants can't change. You don't need them in there necessarily. But for any non-const function, for any function that's like adding nodes and deleting nodes, very probably all of these colors need to be in the code. If not, then your code's probably wrong, right? Like if I don't see size plus plus anywhere within your push, or size minus minus anywhere within your delete, did I remember it? Yes, okay, right? If that line does not appear anywhere within your code's wrong. And I don't even need to look through your code and work out the paper and like, it's just wrong because you're deleting from it and you're not updating the size. And so what I've done is I've like color coded like these things. And so you could look at it and like here you've got gold, you've got red, you got blue, you got green, all 4 of the colors. That's a candidate for the code being correct. Doesn't necessarily mean the code's correct, but at least they got the basics in, right? You got a new here, heads equal to the new guy. Now we could have just said head equals that, which we did before last time. If the size is 0, then tail equals head, list size plus plus. Yeah, this is correct, okay? This is a push front function. Now, here's student code. Now, I TA'd for a lot of years, a lot of semesters, a lot of quarters, definitely. And I developed like this high level ability to like look at code and be like, your code is going to break when you do this. And like, I'd be looking at like 20, 30 lines of code. I'd just be like, all right, once you've inserted things in your code and you've deleted everything out of the code, the next insert's going to cause it to cord up. And like, how do you know that? And I'm like, because your invariant isn't updating. Like, you've got here a pop function, and like, what color is missing from this pop function? Just don't even bother with the code. Just like, what color is missing from it? Pop, in this case, is pop back. Right? This is a pop back, so it's deleting the last element out of a linked list, right? So you got your linked list, and let's add some more elements to it. Why not? Kearney. The previous pointer is this guy. Next pointer is this guy. Next pointer is null. Right? Nowhere within this code, and the pop back function is going to delete the last element, right? Nowhere within this code does the word head appear. And so based on this, I just skim it over. I'm like, nowhere within this code does the word head appear. And so I know for sure, for certain, that when they delete the last element of the list, that head pointer is going to be pointing at something wrong. Okay? Like when, like this is just guaranteed to be wrong because they are not updating the head pointer anywhere. And after you delete the last element of the list, head needs to be set to null. And since their code is actually using a check to see if head is null, to see if the list is empty, this is going to break everything after you've deleted everything and start trying to add things again. Right here, all the colors are in, so good first pass. Here, I could just be like, your code's not going to work after you've deleted the last element. And they're like, what? Like, because normally you have to sit there and you're like, okay, we got this. We're going to go through the for loop. We're going to count how many times it's going to go to the next and go to the next. And you're like doing all this, like, you know, high level arithmetic and stuff. Yeah, if you just learn to think about things in terms of the class invariance, you can immediately say, this code's wrong. You know? And when you write code, you should always look at, like, after you write your code, you should look it over, like, all right, did I update size? Did I update head? Yeah, okay. I got all this stuff in here. All right. So let's go through the actual code and see if we can find out what's going on here. All right. See if this code's correct. So we got a push function, push front. Okay. So what do you guys think of this if statement right here? If head is null and tail is null. So they're trying to check to see if the list is empty. Is this good? What do you think? If head is null and tail is null. Yeah. I mean, technically, this is correct. If he was maintaining his head pointer and tail pointer correctly, this would be fine. Technically, you don't need to check for both, right? Because tail is null and head is null. So I would personally just like delete that. Yeah, because you don't need it. It's redundant. Or you could say if size is 0. Right? Either way. If head is null, or if tail is null, or if size is null, any of those is fine. You don't need to do both, right? Okay. So, but it's just nitpicking. I nitpick a lot. It's not really that big a deal. Okay, so is he successfully newing a new node, right? Because when you do a linked list, you're going to new a new node. Is this student, this is actual student code, is this student newing a new chunk of data off the heap? What do you guys think? Data is being set to new data. The next pointer is being set to null. So if we have an empty list, this is going to create a new node with the data. Let's say we pass in 42, and then the next pointer is null. So is he newing? Is this coming off the heap, or is this coming off the stack? This code here. What do you guys think? When he's got node, he's saying right here new node, right? It says new node. It must be newed, right? Yeah, this is stack allocated memory. This is actually a really pernicious bug that the student did here. So he just named his node new node. And the first time I looked at this, I'm like, my mind just went, oh, he hit new, you know? Nope. This is just a variable named new node, and it's coming off the stack. And so when does a stack allocated variable die, Ella? When does this whole thing here go away? At the end of the scope, boom, right there. So this variable lives between here and here. This is not good because we are taking the reference of the address of the stack allocated variable and saving it. So what's going to happen is we are making a new stack allocated variable, and head is going to point to it, and tail is going to point to it, and then we deallocate it immediately. It gets deallocated right here. And so now head is pointing at something that's been deallocated, tail is pointing at something that's been deallocated. This is very, very dangerous. This is as bad as, like, you know, going on a roller coaster without buckling yourself into the seat belt on one of those roller coasters that goes upside down. It is probably going to kill you just as fast as a roller coaster that you go upside down on without your seatbelt. This is absolutely dangerous. Never ever take. Sometimes you'll take the address of a stack allocated variable, but never preserve it outside its scope. This is actually preserving the address of a stack allocated variable after the variable's died. This is a huge no-no. Don't do this. And the first time I looked at his code, I was like, I don't know, it looks fine to me, because I just saw the word new here, and I'm like, oh, I'm just skimming. I'm like, oh, he's got a new, okay. This kind of stuck out to me because when you're working with pointers, you don't do that very often, actually. Like, you know, usually like when you see me writing code, it's like head equals tail, you know, or something like that, right? Like you don't actually use the ampersand operator all that often when you're doing like linked list work. Like I don't think any of my code actually has the ampersand operator in it. So that should be a sign that you're probably doing something wrong. It's not necessarily a sign, but it's probably a sign. Okay. But this is correct. This part here is good. All right. He's updating the size. That's cool. Okay. Okay, so if we have a list already, it's like, let's say we've got a list with like 42 and like 32 and like -16, and next is pointing at you, and next is pointing at you, and tail is pointing at you, and head is pointing at you. So let's look at this code here. So we're making a new node with the value, let's say we're inserting like 100. Okay, so we're going to make a new node whose value is 100, and his next is equal to head pointer points to get next. So what node is head points to next pointing at? What memory address, which guy are we going to be pointing at with our next? Who is head points to next pointing at? Head is pointing at 42. Head is pointing at 42. This is head's next here. Yeah, it's pointing at 32. Very good. So our next is going to hold the memory address of 32. This is actually what it's doing. Our next is going to be head pointers next. So we're pointing at number 2 in the list, not number 1 in the list, which is wrong. It should just be head pointer. But we're pointing at the second person in the list. And then he's saying head pointer points to set next equals the address of new node. And so he's saying this guy's next is pointing at us. So did the person successfully insert at the beginning of the list? Yes or no? Setting aside the fact that it's going to crash because all of these things are stack allocated and all of them have been deleted actually. The scary thing is this code might actually work for a little while. In fact, his code would work. You'd print the list and it would work. And then you'd print the list a second time and it would crash. And he's like, what's going on? My print function is a const method. It should not be changing the class. But my code is crashing after I printed it the first time. The second time, it crashes. I'm like, welcome to Byzantine errors. This is why you be very careful with your memory stuff. So no, this is not actually a push front. This is push second from the front. Every time he inserts something, it's going to go one after the beginning of the list. So, yeah. Not only did it segfault, but every time he inserted it, it came in second in the list instead of at the beginning. Now here's a pop function. So let's do this. Let's have 10, 20, 30, and 40. Okay, so we got a tail pointer here, and there's really no point to a tail pointer when you have a singly linked list because you can't really do anything with it. And then head is because every time you delete off the back, you have to move tail. You have to start at the beginning and go to the next 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 until you end up one before the tail. So like tail pointers are usually used when you have a doubly linked list because then you just say tail equals tail points to previous and just move it back. You don't usually do this with a singly linked list. Like I said, singly linked lists suck. Okay, so let's go through the code here. So we've already talked about head not being updated properly if the list becomes empty. But let's just go through this. So if head is null and tail is null, return false. What do you guys think of this? Is this cool? It's returning false. The function says it returns int. It's probably returning the value, right? It's like if you were to pop, it's supposed to return the value of 40, I guess. Maybe. Well, if you're trying to pop off an empty list, what should you return? And I guess 0, but like, why would you not write 0? Like, why would you write false? Like, it's just kind of a, like, it's more typing, you know, like it took actually extra effort to write this. So I would actually just change, I mean, it's not going to change anything because false is 0 anyway, but it's just kind of weird to me. Like I would just write 0 there, you know? I don't know. I mean, nitpicking, but like it's still kind of weird. Okay, so here we have int data not initialized, but on the next line he initializes it. This is a great time when you hit Shift J in Vim, and Shift J will move the two lines together. It'll join the two lines so that the data can be initialized. So this should really say int data equals tail pointer points to get data. So we're saying int data equals 40 in this case. So int data over here is going to be equal to 40. It's just basically writing this down. So after we delete the last element, we've got a copy of it. Okay. This is just kind of nitpicky. It's not going to change the correctness at all. But yeah, we should just say int data equals tail pointer points to get data. So we're going to just write down, that's the value we're returning. And down here, in fact, we do return it. So that's good. Okay, so now we're saying node pointer cursor. So we're creating a pointer called cursor. And this cursor is going to, the goal here is that the cursor goes down the linked list and stops here on 30. With the goal being, we're going to move tail back to that one. So this is an order n. It's an order n operation, which is terrible. It's one of the reasons why you should use a doubly linked list. So you can just move tail back once instead of having to go all the way from the beginning. Okay. Yeah, with linked lists, you have order 1. You want to have order 1 inserts and deletes at both ends if you have a doubly linked list. And sorting, something I went over in the previous class. So sorting is order n log n. If I could write here, order n log n. Everybody please type that in chat right now. Sorting is order n log n. Sorting is order n log n. This is for random data. There are faster sorting algorithms if you have non-random data. For example, if you had all heads and tails, you could move all the heads to the beginning of the list, all the tails to the end of the list, and just go through the whole thing, and do it in order n time. But for random data, sorting is order n log n. Okay, this is one of those facts that every computer science major knows. Sorting is order n log n if you've done it right. If you have a bad algorithm, it could be worse. But the best provable, best case time for random data is order n log n. Okay. So, all right. So what do we got here? We're going to go through the list. So if the size right now is 4, so how many times is this list going to go to the right? What do you guys think? Analyze the for loop here. How many times are we going to say cursor equals cursor points to next? So size is 4, right? So list size minus 1 is 3. Did he say less than, or did he say less than or equal to? Ladies and gentlemen, we got him. He did not follow the pattern. He did not follow the pattern. And in fact, that got me in the previous class. I actually did not see that that was less than or equal to. I saw it as a less than because I'm so used to the pattern. I actually missed that in the previous class. I'm just realizing this now. So yeah, this thing is going to execute 4 times. So cursor is going to go to the right once, to the right twice, to the right 3 times, and then point at null at the end of the day. So cursor is now pointed at null. Cool. Neat. This is an order n way of saying cursor equals null. Awesome. Okay, so now we're going to create a temporary pointer that's equal to tail pointer. So we're going to create a new variable called temp pointer. And temp pointer is going to be pointing at the tail. Okay. And then we set tail pointer equal to cursor, so the tail is now pointing at null. That's not very useful now. We meant to have cursor pointing here, right? Like the whole point of it was to be pointing at 30. And so tail should be pointing at 30, but it's not. So tail pointer equals cursor. Temp pointer equals null. So we had preserved this guy, but now temp pointer is just equal to 0 now. I don't even know. This line here doesn't even do anything, right? Because we're immediately changing it here. We then delete temp pointer. Deleting a null pointer actually doesn't do anything. A lot of people think it segfaults. It doesn't. It just has no effect. So this line of code here does nothing, does nothing, does nothing. This is like saying tail pointer equals null. This is an order n way of saying cursor equals null. We then segfault right here. Anytime you use the arrow operator on a null pointer, it will segfault. Okay. So not good. And then he does successfully reduce the size by 1 and then returns data. Now, if this was a less than instead of a less than or equal to, then cursor would be pointing at tail. There's a lot of garbage on the screen. Let's erase it. 10, 20, 40. So if you had this be a less than instead of a less than or equal to 1, then cursor would be pointing here. And then tail would be equal to cursor, which does nothing. 10 pointer equals null. Delete 10 pointer. None of that does anything. Tail pointer's next is null. Well, it's already null. And so at least then it doesn't do anything. It does break the invariant, but it doesn't at least crash. So what we actually need here is less than list size minus 2, I think. If we do that, then it's going to go to the right twice. So we start off with cursor here, and then it's going to go to the right once, go to the right twice, and then temp pointer equals tail pointer. This line here we're going to get rid of. A lot of students think that if you set a pointer to null, it erases the memory or something. It doesn't. Remember, a pointer is just an integer. And so you just set the integer to 0. It's like, all right, cool, it doesn't do anything. You know, so I think he thought that if you set the pointer equal to null, it'd like deallocate the memory there or something. It does. Okay, so if we do this to minus 2, then cursor is now pointing at the one previous to tail. Temp pointer equals tail, so temp is pointing at tail. Tail pointer equals cursor. Okay, so that's good. So tail is now pointing here at 30. Delete temp pointer. Boom, that gets deallocated. Tail pointer's next is null. Correct, that gets cleaned up. List size minus minus, return data. Boom, that's working code. Okay, so only 2 lines needed to be changed. His for loop was going 1 too many instead of 1 too few. You know, like if you're trying to get to the tail, he was going 1 past the tail instead of 1 before the tail. So a little cleanup on the for loop there. This is, again, why you want to sketch everything out. You can actually see it when you sketch it. Like, go to the next, go to the next, go to the next. And then this weird thing here with him he's setting temp pointer equal to tail, then setting temp pointer equal to null. Which makes this completely pointless. And then deleting null, which doesn't do anything. So we just got rid of that thing and deleted the old temp, the artist formerly known as tail. And then tail's next is null, and then good to go. So just 2 lines changed. And he's got a working pop function now, except we're still missing one thing. What color? What color are we missing? Red, right? So we need to put a check in here. If size equals 1, then basically do what I had over here. If size is 1, delete the head, set the head and the tail to null, set the size to 0 and return. So he needed one more case in there like that. Okay. But yeah, just a couple small changes, and his code went from like segfaulting every time to being fine. Now, you got your Bridges Shakespeare due on Wednesday. Your first partnered assignment, open-ended partnered assignment, is coming up on Wednesday as well. You're going to be doing RPG 41. You're going to make a role-playing game involving linked lists. We are off on Friday and Monday, so you're going to have a nice long weekend to work on your RPG 41 and not have fun. And then it'll be due a week from Friday. So it will be a 20-pointer. This will be due on the 24th. Okay, so it'll be a double value assignment. So you get to work on it with a partner. And if you don't have a partner, one will be provided for you. And yeah, so we'll go over more of that on Wednesday. We're already over time now. So thanks again, everybody, for coming out. 2 minutes over. And hope you guys learned a little bit about the linked list today. And we will continue it on Wednesday as well. All right. Thanks, everyone. Peace. No, thank you.